Be problem 13.7, C8H12O3. Looking briefly at the carbon NMR spectrum, we see some signature peaks at 212 as a singlet and 169 another singlet, indicative of two different types of carbonyl compounds. The one at 212 likely belonging to a ketone, the one at 169 belonging likely to an ester or a carboxylic acid. If we go through the IHD analysis, we see I have an IHD of 3 with all of our protons on carbon atoms. With all protons being on carbon atoms, we know that we have either an ester or a lactone. We don't have a carboxylic acid for our 169 peak, okay? And then we have another unit of unsaturation, so we also have a ring. So we have a ketone, we have an ester or a lactone function, and we have a ring in this compound. We also note there's no symmetry indicated in the carbon NMR spectrum. Okay, so all 8 carbons will be unique. Okay, so let's look at some of these units. So 212, we know that we have a ketone group. 169, we know that we have ester functionality associated with that. So let's then go over and look at the proton NMR and see where we are with respect to downfield chemical shifts. So we see we have a peak, and this is a correction, hopefully that made it into your problem set, at 4.2 ppm, a quartet with a coupling constant of 7.2 hertz. We're going to notice that this 7.2 hertz J coupling is related to this 7.2 hertz J coupling at 1.28. Okay, so we have a methylene here, and then we have a methyl group that is J coupled to it. And so that sort of screams out that we may have an ethyl ester. So we're going to assign that as such that we have an ethyl ester, peak at 169 related to the ketone, 61 related to our methylene of the ester. This peak here at 1.28 occurring as a triplet with a J coupling at 7.2 hertz, coupling us back to our ester, which comes at 4.2 as a quartet with a J coupling of 7.2. And then finally, we can pick off this methyl group, the only methyl group in the molecule, and assign that at 14.2 in the NMR. All right, so then everything else we have, we don't have any other methyl groups left, and we have a total of 8 carbons. 3 of them got sponged up by this ethyl ester, so the other 5 must be part of a cyclic structure. Okay, so we have a number of methylenes and then one doublet at 50.8 in the carbon NMR spectrum. We also see this triplet with a coupling constant of 8.2 hertz with one hydrogen associated with it. And so the best structure that we can draw for this is a cyclic beta keto ester structure where we assign this hydrogen at 3.15 as a triplet. So that's a triplet because it'll be coupled to the 2 protons which are drawn here. Those protons will come as part of the multiplets that are downstream. Okay, so we remember when we're looking at beta keto, well, this is a 1,3-diketone. It comes relatively far downfield, and so that's consistent with a beta keto ester, which is kind of at a similar position because it's a methyne, but the ketone is a bit more electron withdrawing as an ester, so that comes at about 55 ppm. Okay, so that finishes off problem 13.7, that we have this beta keto ester structure.